Welcome to Spring LIB.
This is the answer to Chapter 14, problem number 61 from the Smith Organic Chemistry textbook. And in this problem, we're asked to come up with the structures of isomers H and I. And we're given a molecular formula and then IR data and NMR data about each of the isomers. And so I've just written out everything that we've been given for each of these isomers in black. And then I'm going to show my work in green just to distinguish what we're actually doing here. Okay, and so I think the first thing to do whenever we're given a formula and asked to derive a structure, the very first thing to do is to calculate the hydrogen deficiency index, or the degrees of unsaturation for each of these molecules. And so remember, that is going to be 2 times the number of carbons plus 2. Oops, and I don't know why I drew a C there. So it's going to be 2 times 8, since we have 8 carbons. So 2 times 8, there we go, plus 2. Minus the number of hydrogens. And so in this instance, we have a nitrogen. And so we also need to add 1 for each nitrogen that we have. So we have 1 nitrogen. So it's going to be plus 1. And then all of that is going to be over 2. Okay. And so there we go. So 16, 18, 19 minus 11 is going to be 8 over 2 equals 4. And so we have 4 degrees of unsaturation here. And so that tells us we're going to have a number of rings or a number of double bonds or really pi bonds that add up to 4. And the other thing is, whenever we see an HDI of 4 or more, we should be thinking aromatic ring, because 4, 1 benzene ring accounts for 4 degrees of unsaturation. And I apologize, I'm experiencing some really bad lag here. So that try to write this again so that it's legible. Okay. All right, so my apologies for that. Let's try again. So whenever we see an HDI of 4 or more, we should potentially be thinking a benzene ring or an aromatic ring. Okay. So then that's going to be the same for both of the isomers since they have the same molecular formula. So we can start looking at the IR data. And so unfortunately here, the IR data doesn't tell us very much that we don't know already. So these 2 signals here at 3365 and 3284, these are going to be from NH bonds. And so I guess that does tell us, that we have a primary amine here. So we have 2 NH bonds. The signal at 3026 wave number is going to be from a sp2 carbon. Oh my goodness. Sorry, I don't know why this lag is so bad. So a CsP2 carbon bound to a hydrogen. At 2932 wave number, that's going to be a CsP3 carbon bound to a hydrogen. At 1603 wave number and at 1497, these are both going to be from the aromatic ring. So I'll call these benzene signals. Okay, and so the NMR data is going to be what we're going to have to rely on to actually tell us how this molecule is put together. And so the first signal that I'm going to actually look at is this signal at 7 ppm. It's a multiplet and it integrates to 5, and that's really key. So we were already suspecting the presence of an aromatic ring from the hydrogen deficiency index, and then again from these IR signals. And so this multiplet at roughly 7 parts per million with an integration of 5 confirms that. This is a monosubstituted aromatic ring. And we know that it's monosubstituted because of the integration of 5. Remember, if it was just a benzene ring floating by itself in space, it would have 6 protons on it. And so with one substitution, it has an integration of 5. So then looking at the other signals, we have 2 triplets and a singlet. They each integrate to 2 protons. And so what they're going to tell us, so the singlet at roughly 1 ppm integrates to 2, so it's not split by anything. And so again, from the IR data, I was already thinking we might have an NH2 group. And so the lack of splitting leads me to believe that these are the protons from our NH2 group because they're not splitting. So then we have these 2 triplets that integrate to 2 each. And so they are going to be from methylene groups. So CH2, both of them. And so when we put all of these pieces together, we get something that looks like this. So we have our aromatic ring. Oh, man. Again, I apologize. I'm not sure why the lag is so awful today. So let me redraw this. Okay, so we have our aromatic ring. Okay, aromatic ring, monosubstituted. So there's one of our methylene groups. There's the second methylene group. And then here is our NH2. Okay, and so that fits with all of the data that we have here. And so that's the structure of H. So then for I, we're just going to do the exact same thing. So we have the HDI already from the previous page. And again, it's 4. So then looking at these IR signals at 3367, that's an NH. Oops. Do this in green as well. So NH. And at 3286, that's an NH as well. At 3027, that's going to be a sp2 hybridized carbon, CsP2. H2962, that's a CsP3. H, and then the last 2 signals again are due to the presence of an aromatic ring. And so again, looking at the signal around 7 ppm, that's a multiplet that integrates to 5. So again, this is going to be a monosubstituted aromatic ring. Oh my God. Again, I do apologize. I am not sure why this isn't really working for me today. Aromatic ring. Oh my God. Okay, so there's our aromatic ring. So then we have 3 more signals. And so looking at the first one, this is a doublet. It integrates to 3. And so this to me is a methyl group. So this is a CH3. with one neighboring proton, which is why it's split to a doublet. And so we have a signal that integrates to 1. This third signal here at 4.1 ppm is probably a carbon with 3 bonds to other carbons and 1 proton on it. So probably like that. And then the second signal at 1.5 ppm is probably a methylene group. Okay, and so if we try to, oh no, you know what? It's not a methylene group. Okay, so there's no splitting on that second signal, and that would be too many carbons, right? So we have 6 carbons in the aromatic ring, and then a 7th carbon at the 4.1 ppm signal and an 8th carbon at the 1.4 ppm signal. And so we are out of carbons at this point. So this 1.5 ppm singlet that integrates to 2 is probably the protons on our nitrogen. And that's backed up by the fact that it is a singlet. It's not showing any splitting. Okay, yeah, so that makes more sense. And so when we put these pieces together, what we get is this. So there's our aromatic ring. Here's our tertiary carbon. So this carbon has 1 proton on it. And then it also has, let me lower this so that it's a little easier to see. Okay. So it has 1 proton on it, and then it also has this methyl group. Okay. And there is our nitrogen with its 2 protons. And then here we'll draw that other hydrogen in there. Okay. And so that structure is consistent with all of the spectral data that we have for isomer I here. And it is indeed the correct answer. And so this is I. And then again, H is over here. So this is H. And that's the answer to chapter 14, problem number 61.